show you how to determine whether a number sequence or a pattern is a linear or quadratic or exponential, and the main emphasis will be on exponential. So in the first situation, we are trying to model the number of aphids growing on rose bushes each day, and you can see that the x variable is the number of days and the number of aphids is the y variable. Now, in any of these number sequences or patterns, the first thing to do is to figure out what the first difference is, which is simply the difference between 6 and 3, 12 and 6, 24 and 12. So this would be 3, this would be 6, this would be 12, this would be 24, and this would be 48, and this would be 96. So the first difference is not constant, therefore this tells us we do not have a linear function. So we could either have quadratic or exponential, but we do not have a linear. So we do this. Now we want to look at the second difference. So the second difference here would be 3, 6, 12, 24, and 48. So again, the second difference is not constant. First difference is not constant, we do not have linear. Second difference is not constant, so we do not have quadratic. So in this particular case, we're looking at an exponential function, which would have the form y equals a times bx plus or minus c, where a is the y-intercept, b is the common ratio, and c is the asymptote on a graph. So when you've discovered that you potentially have a exponential function, you want to find out what the common ratio between the y values are. So that would be 6 divided by 3, which would be 2. 12 divided by 6 would also be 2. 24 divided by 12 would be 2. 48 divided by 24 would be 2. 96 divided by 48 would be 2. And 192 divided by 96 would also be 2. So this ratio is really going to be the b value in our exponential expression. So we have now, in this particular case, an equation that's going to be y equals some value a times 2 to the power of x and there's going to be some constant c as well. So if I just copy that first and put this here, then I can change this to 2. So there's the first. We know that the common ratio is equal to 2, which equals the value of b. So now we have to try and find out what a is. And a is where it cuts the y-axis, or what is the value of y at x equals 0, which would be one step back from here. Well, everything's going up in 2s, so if we just simply take the value of here at x equals 1 and divide that by the common ratio, or b, so 3 divided by 2, that would be what the y-intercept would be. So here now we can take this equation and we can now fill it in a little bit more. We've got now, we can put in here 1.5 times 2x, and now we just have to find out what the value of c is. And to do that, you just need to carry out this first part here. So if I go, just copy that first piece and put it in here and go ahead. So 2 to the power of 1 is 2 times 1.5 is 3. 2 to the power of 2 is 4 times 1.5 is 6. 2 to the power of 3 is 8 times 1.5 is 12, and so on down here. So this is actually our constant, and it tells us that there is not going to be any c term in this particular case. So our final equation is going to be y equals 1.5 times 2 to the power of x. And we can see this when we graph it as well. These things all tie into the graph. So our final equation is going to be that. Now if I went ahead and plotted this on a graph, we would get the following. So we had y equals, at x equals 1, we had 3. X equals 2, we had 6. X equals 3, we had 12. X equals 4, we had 24. X equals 5, we had 48. X equals 6, we had 96. And x equals 7, we had 192. So here you can see that this is the plot of the graph, and you can see that it's approaching y equals 0 here. And if I type that in, y equals 0, you can see that all of these points are approaching that, but not quite getting there. And so I could actually now put in the function here, y, and this should be y1 equals a times b to the power of x x1 plus c, and you can see again that a is 1.5 and b is 2, so our equation is simply y equals 1.5 times b to the power times 2 to the power of x. So that's the first problem. The second problem here is that if we were modeling the area of lily pads covering a pond per day. So again, we'd go ahead and do the first differences. So you can see that we've got 12. Here we've got 24. Is it 24? Yep. The next one would be actually 54 minus 18 is equal to 36. So there's 36. The next one will be 108. The next one will be 324, and the next one I'm not going to work out. So the first difference tells me we don't have a linear pattern because it's not constant. So if I do the next one, we've got 24, then we would have 72, and the next one we would have 216, and so on. So the first and second differences are not constant here. So now we know we've got an exponential, so it's the same situation as number 1. So now we're going to look at the ratio. So I'm going to divide 18 by 6, which would be 3. I'm going to divide 54 by 18, which would also be 3. I'm going to divide 162 by 54, which would also be 3. This would be 3, and actually these ones, this ends up being 3. So what this tells us, in this exponential function, the b value is going to equal 3. So I'm going to substitute that in here, and I'm going to try and then find out the rest of the equation. So I'm going to take this equation and I'm going to paste it here, and I'm going to change this to 3 because I know the common ratio. This is the common ratio. Now I'm going to find out what A is, and that's A is going to be equal to the 6 divided by the common ratio. So it's going to be 6 divided by 3, which is equal to 2. And so I now know here that my equation is now going to be y equals 2 times 3 to the power of x, and I've got to look to see if I've got a c value. So if I take this and copy it and paste it in here, if I go 3 to the power of 1, that's 3 times 2 is 6. If I go 3 to the power of 2, that's 9 times 2 is 18. If I go 3 to the power of 3, that's 27 times 2, that's 54. If I go 3 to the power of 4, that would be 81. 3 to the power of 4 would be 81, and 81 times 2 would be 162, and so on. So in fact, this is telling me that there is no c value at all. So I can now change the equation to be that. It can be y equals 2 times 3 to the power of x. And that's my final equation. And again, if I model this on a graph, so now I'm going to save that one, and I'm going to add a new blank. I'm going to put in a new table. So we had 1 and 6, 2 and 12, 2 and 18, 3 and 54, 4 and 162, and 5 and for 86. So I've got my table. I'm going to now change the scale here. I'm going to go from 0 to 10 on the x-axis, and I'm going to put in number of days as my label there. And this one I'm going to go change to 0, but I'm going to go up to 500 on this. I'm going to change it to that. And I'm just going to click out a bit, and you can now see the graph being an exponential. And again, if I put in y equals 0, you can see that again it's approaching that but not getting there, because we know that this should be 0, 3 back here. I can put that in 0, 3 there. And now I can model this. I can go y1 equals a times b to the power of x1 plus c, and we can see that this would be 2 and this would be 3. Actually, if I took that out, probably come right back to, so we can see it's 2 and 3 there. Actually, and so that's the A value, that's that, and the C value. So it's 2 here. So that should be 0, 2 actually, 0, 2. And that is our equation. So the graph and the tables tell us the same information. I hope that helps you with these simple